now we're ready to talk about sources. I think you have picked up from my previous slide that the reason for knowing about sources is because the source you were interested in kind of determines what's happening in the time frequency plane, as well as the kind of frequency choices that you end up making. And so from my highly simplified engineering perspective, I tend to think in the time frequency plane. So the horizontal axis here is the duration or period over which you see flux from a source. And the vertical axis here is the occupied bandwidth of a source. And I see four quadrants when I think in these terms. Most folks readily identify or comprehend this lower right quadrant, which are sources which are slowly varying or not varying at all, and are relatively narrow band, hertz to megahertz. And those are primarily spectral lines. And everybody here has probably heard spectral lines. So there are a whole list of important ones: deuterium, hydrogen, hydroxyl, and the list goes on and on. I'll give you the list if you don't have it already. Much higher frequencies, millimeter waves, we have abundance of molecules that produce these forests of spectral lines. So this is a big deal, pretty easy, I find, for most people to understand. What I find a lot of folks don't understand who aren't familiar with radio astronomy, but are engineers, don't realize about continuum. Continuum is another way of saying that it's a source which produces flux at all frequencies in the RF spectrum. So this includes backgrounds, sources which are distributed over the entire sky, like famously the cosmic microwave background is one. The galactic synchrotron background is another important one. And then there are discrete sources which are of small angular extent, energetic objects. Confusingly, SNR here means supernova remnant, not signal to noise ratio. So just like any other discipline, prepared to be confused by the acronym and symbol redundancy. Here, signal noise ratio, here SNR means supernova remnants. AGNs are active galactic nuclei. These are things which produce broad spectrum emission, and you learn about them by observing different frequencies. Clouds and nebulae, these are abundances of materials, gas-like states that also radiate in the continuum, typically because they're thermal. Stars, which, by the way, I should point out, stars in radio are normally very, very hard to see. And if you can see them, it's because they're doing something very interesting. And I'll give you an example. But stars are not the same abundance of effort in radio astronomy that they are in other disciplines, because they're relatively hard to see, again, unless they're doing something interesting. We tend to categorize this continuum emission in three flavors, and this becomes important a little bit later. Thermal emission, which Joel has told you at length about, is simply what you get from the random motion. Again, all radio emission is due to the acceleration of charged particles, right? So if those charged particles are being accelerated because they're going in random directions as they have heat, that produces one kind of emission. If you have the organized acceleration of electrons, very distinct from thermal, that's quite often the synchrotron emission would be the thing we're referring to there, has a very different spectrum. And then there's this third thing called free emission, which is neither thermal nor organized emission or organized acceleration of charged particles, but rather interactions between particles where they're changing directions, and that aggregate effect of changing directions produces a different kind of spectrum. And these, of course, give you valuable clues to what the sources are and their underlying physics. Over here, short things, which occupy essentially all bandwidth, are pulsars. You see I've listed 3 times. I guess that can be interpreted as a indication of my enthusiasm for these particular sources, but it's true. Pulsars are enormously important in a whole bunch of applications. A lot of telescope effort and money goes into looking at these things. Pulsars can be purely periodic. They can have very short one-off emission. That one-off emission can be down to nanoseconds. So one of the most astounding things I think I've ever seen is at Arecibo once observing nanosecond pulses from a pulsar. And you think about it, a nanosecond pulse had to originate from an area that was no more than tens of centimeters or a meter across, right? So you're seeing things that are happening on very small time scales or very small distance scales, tens of light years away. That's just fascinating. But to see those, that's obviously a short integration time. Pulsars do all kinds of other weird things. There's some class of pulsars for which we don't see every pulse. We just see them kind of very intermittently and maybe very sparsely. They do things like they null for periods of time, then turn back on. All these things provide valuable clues that have scientific relevance. And then, of course, FRBs, some of those may be pulsars, but there's a whole range there's these things which are now of great interest, which are short pulses, they're dispersed, and they're short integration times, but they have large bandwidths. The fourth quadrant here, the one in the bottom left, if it's short in time and it's limited in frequency, that is the hallmark of technology. Natural astrophysical sources typically don't end up down here. If you see it, it's typically technological. So if it came from the Earth, that's probably interference. If it came from somewhere else, collect that data, verify it, and submit for your Nobel Prize because you just discovered ET. So there is the range of possible sources. So continuum sources, again, I have to say a little more about. They all have different spectrum. And the spectrum gives you information about the sources. Typically what happens here, and note the scale here, I'm going from 10 megahertz to a terahertz. So we're looking at an enormous range here. Typically when the slope is doing this, it's negative. Those are synchrotron emissions. It's typically the organized acceleration of electrons. When you see spectra doing this, that's thermal. That means you're seeing something that's hot, for example, Venus. And then you see these sources that do something different. So the spectral index, as we say here, the rate at which it's going up or down in spectrum, or the inflection points tell you very important things about the spectrum. In fact, that might be the only way that you can tell what it is you're looking at. And by the way, you're getting indications of flux density here. These are very strong sources. Let me be clear about that. 10 Janskys is very, very strong, unambiguous, not hard to see at all. When you get close to the bomb edge of this plot, you're starting to talk about things that take a little bit more work to see. And then I should tell you now, 10 micro Janskys is probably about the weakest kind of sources I can think of. I can't really find examples of anything less than 10 micro Janskys. 100 micro Janskys is more common. A millijansky is pretty typical. I'd say tens of millijanskys is common. So just to give you an idea of flux scales. So here's an example. This is a galaxy, M82. If you're an astronomer or you're interested in astronomy at all, you might know about M82. It's a pretty well-known galaxy, certainly well-known to radio astronomers as well. But we see M82 primarily a synchrotron emission below 100 gigahertz or so. Above 100 gigahertz or so, we see it primarily as thermal emission. And then in between, this inflection point is blunted by free emission. So you can sort out what's going on with this galaxy, despite its great distance, by looking at the spectrum. And you can infer from the spectral range here that you need a lot of frequency points to figure this out, right? I mean, this curve is not apparent until you've measured frequencies all along here. And these measurements, these markers all pertain to measurements that people have made. I can assure you that those measurements were not all made at once. A lot of effort goes into doing this. And I should say, this is a relatively strong source. It's 1 Jansky, 1 to 10 Jansky. It's just within this range here. Again, it's routine to see things which are on the millijansky scale. So you can imagine how much more difficult it is to figure out this curve when you're dealing with these long integration times, where the information in where the spectral index is the thing which is telling you what you need to know about the source. Here's another example for the need for huge bandwidth. I just love this result. This is one of the few cases actually where you can see stars in the radio productively. This is YZ Canis Minoris. This is a inconspicuous star optically, but you can barely see it as a continuum source. But it gets busy in the radio, and it does. It's a flare star. It actually produces dynamic radio emission in the observable radio spectrum. So what we have here is a time scale of minutes across the bottom, 0 to 10 minutes, a frequency scale that's going from about 1 gigahertz to about a little bit beyond 3.5 gigahertz here. And it's color coded so that red and blue represent the two left and right circular polarization. So the Stokes parameters have been calculated for this dynamically, and whether it's red or blue, saying whether it's right circularly polarized or left circularly polarized. And that's typically how these flares are observed, is in terms of their circularly polarized emission. You see the scale here is not a joke. That's millijanskis. It's negative because they're using the sign of the flux to indicate whether it's left or right circularly polarized. So it's not that there's negative flux. Nothing's being sucked out of the telescope. It's just indicating the sign of the sense of the polarization. What should be remarkable to you about this is that all that spectrum is really needed to understand what's going on here. I mean, here are features in the dynamic spectrum which are important and tell you important things about what that star is doing. So if you understand how to read these things, you can ascertain just a wealth of information about this particular object. You'll also note that there are white stripes here. Welcome to the first order defense against RFI in this kind of astronomy. Most kinds of astronomy is you don't observe or you wipe out affected spectrum. So I'll tell you with 100% certainty that that is some combination of Inmarsat and GPS and Iridium there that's making these people want to wipe out that band. And then this is probably, I think that's probably broadcast radio satellite. I think that's XM, maybe, I don't know. In any event, it's a downlink broadcast satellite that just kind of has enormous flux and really kind of complicates these observations. So he's just wiped it out so you're not distracted by it. I can certainly I took out 3 or 4 other examples of this, but I think this illustrates the point that all the frequencies are getting used here. They're productively used, and you see kind of what you have to deal with in terms of integration times. Here, the integration time has to be really fast. If it's not, you miss the detail. Now, pulsars. Pulsars, in some sense, are continuum, in the sense that they have spectrum that looks like continuum sources. In fact, you can tell pulsars are not thermal here because you see their spectra going down. That is a clear indication of the organized acceleration of charged particles. You see an indication here of flux density. This is in Janskis. So pulsars tend to be weakish sources, but they're much weaker at higher frequencies. So you go to higher frequencies, they can be very hard to see. Typically, they peak somewhere between 100 megahertz and a gigahertz or so, as these two do, which means that's the place to look for them. If you're trying to detect them, you want to be somewhere between 100 megahertz and a gigahertz or so. But there's then 20 different reasons why you might not be able to go there, including interference might be one. Just in case you don't know, a pulsar is an end product of a star's life, in which case, one of the possibilities, which the star has collapsed down to a neutron star, these ultra dense things, it's spinning around, it's producing a beam of organized emission. As that beam sweeps past the Earth, you see it as a pulse. Because the distance between us and the pulsar is not empty, but rather is a plasma. It consists of free electrons. That pulse gets dispersed. So you see the highest frequencies first and the lowest frequencies last. And even though space is almost nearly empty, there are enough of those electrons around that the dispersion over these distances is significant. In fact, it's so significant that if you don't account for it, you don't see it. So the way pulsar observing gets done is you observe over a large range of frequencies. Here it's 1200 to 1550 or so. You see the pulse being chirp. That's all because of the interstellar medium. That's not the pulse itself. The pulse itself looked like this. So to see what the pulse was actually producing, you have to de-chirp this spectrum. You have to shift the high frequencies, the low frequencies, delay the high frequencies so that they line up with the low frequencies. So that creates this issue of de-dispersion. To productively observe these things, you have to be able to, in real time, often, do this de-dispersion transform, which is itself computationally quite difficult to do. Okay, spectral lines. I promised more on spectral lines. This is the obligatory list of spectral lines. It seems like whenever everybody wants to talk about radio astronomy, this is actually one of the slides that shows up in every single talk. For the right reasons, they're important. These are rest frequencies here. These are the frequencies before things get Doppler shifted around. This is not a complete list, and the list has been truncated here at 90 gigahertz or so. So, for example, the incredibly important CO lines aren't there, but I have so much space. The intent here is simply to show you that there are such things, and so you know what's going on there. What they look like when you observe them, I like this example a lot because it kind of tells you both what they look like and also how they get used. So first, these are spectra. This is power, density versus frequency. No astronomer would ever list it as frequency across the bottom. They would list it as kilometers per second. That's velocity. And the reason is because if you think about what Doppler is, it's a relationship between the velocity of something and the frequency of something, right? So what they're actually doing is they're plotting frequency, but immediately converting it to the velocity by solving this equation. And that's useful because that is actually the speed at which this thing is moving along the line of sight. So whereas the hydrogen line is in fact very, very narrow, as soon as if you have a lot of it and it's all coming into your beam and they're all moving at different rates within your beam, you see things that look like this. So it tells you the relative abundances of hydrogen, the column density of hydrogen as a function of Doppler shift. And that has enormous astronomical significance. So a lot of this gets done. And that's just one line. That's the hydrogen line. You could do the same measurement for a different spectral line. In this case, it's carbon, CO. The CO10 transition, one of the carbon lines, is at 115 gigahertz. And you can detect that. It gets Doppler shifted around as well. And if you were to plot this in frequency, of course, it'd be way off to the right side of the page. It'd be close to 115 gigahertz. But what we're doing here is converting it to velocity. So here they can be plotted together. And so you can see, okay, the 100 kilometers per second here is 100 kilometers per second here. So you're seeing now the relative distribution of abundances and velocities for these two different materials. And for example, in this case, what it tells you is that you're seeing a lot of hydrogen. It's diffuse. It's kind of spread around the beam. It's going at different speeds, but you see all the Doppler shifts here. Whereas when you look at CO, you see there's a few discrete components and it fills in only at very low levels, which tells you here you're looking at discrete things in the field of view. And already you've got a ton of information. You now know that CO tends to be chunkier and the hydrogen tends to be more spread out. And this again has important information in terms of identifying what you're looking at, in terms of characterizing it, and so on. That was galactic hydrogen. Here's intergalactic hydrogen, extragalactic hydrogen. You can tell right away this is extragalactic hydrogen because you see that this line is occurring not at 1420 megahertz or so, but rather at 1416 megahertz or so. Once again, it can be converted to kilometers per second. So that's normally the way it's shown. You see this thing is moving compared to the other spectra I just showed you. I like showing this one, especially to engineers. And here's why, is because you see that the hydrogen from this thing looks like this horn shape. As the caption says here, that is the typically what you see for a spiral galaxy. But I think wireless engineers recognize this too. If you know anything about mobile radio spectrum, you know that if you have a source moving through a high scattering environment at a sufficient sufficient speed, you see a Doppler spectrum, and that is the Doppler spectrum that you typically see. It peaks at the extremes, it dips down in the middle. So wireless engineers should recognize this spectrum, and it happens for the same reason. The spiral galaxy, some of it's coming towards you, some of it's going away, and you see the same shape for the same reasons. Note the flux. This is just a few tenths of a Jansky, comparable to the number I worked out at the very beginning of this presentation. Right, so 100 millijanskys or so is getting interesting in terms of low flux densities. Molecular lines, when you get to higher frequencies, what happens is you start to see these more and more complex molecules. So more complex, here's some numbers, here's some chemical formulas here indicated along here. This is looking in a particular direction for a known source. It has abundance of these things. Observed frequencies, so you see this around 90 gigahertz or so, and you just see one of these forests I alluded to. So this becomes more and more, this is a quite complicated thing to look at. If you are an expert in this area, you learn to identify these things readily. The rest of us just kind of marvel at people's ability to keep track of what all these lines are for. And what I always think about when I look at this, it looks to me like the interference I see at lower frequencies. So you can anticipate that the reason this gets done productively now is because there isn't so much narrowband interference going on at these frequencies. This is something a lot of people worry about. So if we talk about time and frequency, there's also the angle domain. Of course, we can image in radio astronomy, and a lot of this is, there's a lot of information, of course, in the image in the angular domain. So what I've done here is kind of identified some categories of sources again, and then the kinds of instruments that are used to observe these things. So, you could think of global things like cosmic microwave background. They're everywhere. Yeah, that's everywhere. At some level, it's constant. At finer angular scales, you can resolve some lumpiness. But these are things you can observe with relatively small dishes. When you get to larger or finer angular resolution being required, then you need larger apertures. When you get to things which are on the scales of arc minutes or so in extent, kind of the same, say, angular extent comparable to that of the moon when you look at it in the sky, then you need dishes which are going to be quite a bit larger. And then you start thinking about things like interferometers. Why do we think about interferometers? Because it's hard to make dishes which are hundreds of kilometers in extent, right? At some point you have to give up and you have to say, I'm going to get my angular resolution by sampling the much larger aperture that gives me the angular the resolution that I want. So here's a scale of instruments going up from small dishes to big dishes to small interferometers to large interferometers. VLBI stands for very long baseline interferometry. Now you're talking about distances of hundreds to thousands of kilometers. And then, of course, a lot of people have seen this. That's an image of the environment around the supermassive black hole in the galaxy M87. This is a recent headline news story. Showed up in the national news. Can't get more famous than that. Made by the EHT. EHT stands for Event Horizon Telescope. That's a VLBI system that covers essentially the diameter of the Earth, overlaps North America, uses some telescopes in North America, as well as in Antarctica. So this is what you need to make resolutions on, make images with that kind of resolution, which I think, I should have written this down. That's probably tens to hundreds of micro arc seconds. Yeah, I think it's on the order of 20 or 30 micro arc seconds. So that's pretty fine imaging. But then there are also, again, sources which are just too small to see. Pulsars tens of kilometers across. No hope of any of these instruments ever resolving it as an image. But nevertheless, we still use interferometers because we want to know precisely where they are. That precise location is important. Maybe not imaging it, but knowing exactly where it is in the sky, because that gives you the possibility of association. And for example, if you know the pulsar is a particular point, and you know that corresponds to a galaxy, pretty good evidence that that pulsar is in that galaxy.